Now I'd like to introduce to you Professor Heinrich Meyer, whom you probably know, who has been visiting here for a while. He's a professor in Aachen, Germany, and he very kindly organized this event, and so I'll ask Heinrich to introduce the various speakers.
Thank you very much. Nani, well, we organized it together, and it's a great pleasure to welcome you here. With our three speakers. The first speaker is Joachim Kunkel. I happens to know all of them very well. So Joachim, I don't need a slide to tell you what he did. He was a student in Aachen, student of mine in Aachen. Then we co-founded a company called Cadis, which we then sold to Synopsys. And Joachim continued to go with Synopsys. I think at that time, Joachim, the company was about 200 people maximum, Synopsys. So he's now responsible at Synopsys on the top level management for IP. That's a $430 million yearly business, and we're very excited to listen what he has to say us on the IP and all what he's doing. Okay, your line, please.
Okay, thank you very much, Heinrich, for your kind introduction. And first of all, thank you for having me here today. I look forward really to the discussion portion, which is the one where I'm going to be learning something from you, which is really the main reason for being here. And if I can find the port, okay, this seems to work. Okay, here we go. So the title of my talk today is Designing Analog Mixed Signal IP Beyond the 28 nanometer process. The reason this is quite interesting, and I'm going to be talking about a number of things, but the reason that this is quite interesting is that obviously highly integrated SoCs continue to follow Moore's law, and they are progressing towards smaller and smaller geometries. And as we're getting into smaller and smaller geometries, it's getting more and more difficult to do design. Now, what happens is on the digital side, we're able through automation, through EDA, design automation, to hide most of the effects that are happening in the physical implementation behind the tools. So as a designer, you pretty much are being presented an abstraction that hasn't really changed from the very early days. Of course, it gets more complicated to meet timing, etc., 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 but nothing has fundamentally changed. When you are dealing with analog mixed signal design, is when design automation has not really been able to hide the physical effects, and you have to deal with the physics, and you pretty much have to deal with the physics just by confronting it with intelligence and with creativity. And I want to talk a little bit about the things that happen there. So before I do this, though, I want to give you a little bit of an idea as to how all of this fits within the company. So if you look at Synopsys as a company, we think about us being active in 5 areas. We historically started out in the area of implementation. Some of you may have heard about a product called Design Compiler, and that's the way that we started as a company. This was around 1986, if I believe. Completed the flow on the implementation side, completed the side on the verification side, and this is pretty much what we call our EDA business. Implementation, verification at all different levels, digital and analog and custom. And then we added a number of components to it. We added IP and system design to that. And we added also an element of going down into physics, going down into manufacturing. The piece that I'm responsible for in the company is this one here, which is called system design and IP. And obviously, this for us was moving into what we call an adjacency. It was not our classical business that we were established in, but was an attempt to move into a related area in order to try to grow the company faster. And these are bets that you make, typically. Some of them work out and others don't work out. In this case, I think we did pretty well. And what I've plotted here is just the revenue of the company. So that's every quarter starting in Q1 of 2006, going all the way to our last quarter, which was Q1 of 2013. You can see 100% of the revenue of the company here. Okay, then we break 100% down into the different elements. And the purple is kind of our typical business, what we call core EDA. And then the green one is the IP and systems portion, so kind of the new things that we started getting ourselves into. And by the way, this started with the acquisition of this company that Heinrich and myself had started in Aachen a long, long time ago and sold to Synopsys around 1994. And obviously at that point in time it was much smaller than the green bar here. So it took quite a while until this started materializing. The orange piece was the manufacturing piece, and then we have a little bit of services on top, which is just selling design services. What you can see is that actually we've been very successful because the company as a whole has been growing, and the green portion has been growing much, much faster than the purple portion. So that's good. So from a business perspective, adding something new to EDA, adding IP and systems, has been a bet that we made as a company that worked out for us. Not all of these bets work out. We had hoped that, for instance, the orange piece would also grow much faster. If you look what happened, pretty much remained constant. You don't win them all, right? So the perspective that, now in the different business units, obviously we take different perspectives of a chip in order to define our strategy. And we kind of all abstract things and simplify them somewhere differently. So what we do with IP is basically we enable the design of big chips. And the way that you enable that is you say, like, look, I mean, all of these chips, and that's a perspective, there's many different perspectives of chips, as you will find out today. One perspective is all of these big chips, they just consist of a bunch of building blocks. And most of these building blocks are pretty known things these days. You can put names on these things, and some of them are exactly the same across many, many chips. I tend to joke when I'm going to customers and tell them, look, I mean, all of these building blocks here, I mean, you can buy all of this stuff from us, but obviously if that's the only thing that you put on your chip, and this is not realistic, right? Your chips are probably very, very different because you want to differentiate them. And they look at me and say, actually, they look very similar to this. Yeah, we have a little bit of a secret sauce here and there, but basically this is what it is. And the reason that this is what it is that what's happening within the chips, within the little chips, is exactly the same thing that's happening in the systems world. The only way to build big stuff is to build it from smaller stuff. And in order to make this cost effective, the smaller stuff has to be pretty much the same, because otherwise everything is a one-off and that makes it very expensive. So you build big computer systems by buying a bunch of servers and a bunch of PCs, and there's not that many brands, right? There's a few, and then you look into all of these boxes and they have the same processor, and they have the same this and they have the same that. The networks, though, are relatively different. It's exactly the same thing on systems on chip. They consist of a bunch of building blocks. I've depicted many of them here. And you connect those building blocks. In order to be able to connect stuff easily, we all know that we need to agree on interfaces. So we need to agree on the on-chip interface, on the on-chip fabric, and what those interfaces here in particular look like. Because otherwise there's no plug and play. It's the Lego idea, right? And you may think that, well, so that's fine. I mean, of course, everything uses amber buses, etc. That is today. But if you go back historically, it's just 5 years ago, 5 or 6 years ago, this picture was very difficult to implement because there were a variety of buses available in the industry, which means that you could build building blocks, but they would not plug onto the bus immediately. So you could not mix and match. Over time, the standard in the industry for on-chip communication has been materializing, and this has really been the thing that has fueled the AP business. And I'll show you a little bit more. So basic idea, you build big stuff by reusing smaller stuff that you already have. You agree on the interface, on-chip interfaces, and then you can take it from there. Now the other thing that's happened, and I'm trying to depict this here by the pale blue, is that these chips in the meantime are full of processors. Some of them are very well known, right? I mean, you buy an iPhone and then everybody wants to know, is this the A4 or the A5 or is it an A6? And in case it's an A5, what's the ARM processor that's on that, et cetera, et cetera, et cetera. And they're very well known. The thing that's not that well known is that there's a truckload of other little processors running on this iPhone. Some of them actually are ours, and I'm not going to tell you where they sit, because if I know, I can't remember it. And because of this, what ends up happening is that the hardware itself, so the chip itself, has become the execution platform for the software. You take pretty much any chip today, you apply a reset, and it doesn't do anything. Well, the only thing that it does, it goes to the memory and tries to find an instruction. And if there's no instruction, that chip is just dead. And the amount of software that's running on it is becoming huge. In fact, the effort to develop the software relative to the effort to develop the hardware, people talk about it's become 50-50 by now. Some people say, no, it's much more than that. It's like 70% is software development effort, 30% only is hardware development effort. It doesn't really matter. The difference is that the amount of software has become very significant. And then for us as a company, of course, this opens up the opportunity to develop, to sell customers a bunch of things to deal with this issue. So our business basically has become the business of selling customers IP building blocks so that they don't have to design these standard stuff themselves, and to offer them tools that allow them to deal with the issue of software development, hardware-software integration, and system validation. Okay? The other thing that's become quite interesting is that an SoC actually doesn't do anything unless you have the software that runs on the hardware. In the IP space, the same thing has happened. We're starting to have IP building blocks or functions that actually consist of hardware and software. And I'm trying to depict this here. So for instance, we have an audio subsystem, and this one consists of a digital processor, obviously, some analog interfaces, typically with A to Ds and D to As, obviously, otherwise there's no way to get the sound in and out, mixers, etc., and all of the software that has to run on that. So these are the speech codecs, these are all the sound processing, equalizers, etc. So the idea, and that's pretty much, I told you that a system at the big level, for instance, a network consists of a bunch of boxes. You look into the box, well, the box is hardware and software. You look within the box, there's a bunch of chips in there that consist of hardware and software. You look into the chip, and actually what you find is a bunch of IP building blocks or IP subsystems that consist of what? Hardware and software. So it's kind of a fractal nature of the whole thing. You keep on peeling the onion, you keep on seeing the same thing. Functionality today has become mostly a combination of hardware and software. So let's look a little bit into what's really driving the development. So the business that we've built has been based partly on organic growth, but also partly of acquisitions. We started out really going deeply into interfaces, then we added more on the interface side with high-speed SerDes. I believe Rabi's going to be talking a little bit more about that. I also will be covering some of this here. And then later on, we added some analog, and then we added some things like memory and logic libraries and processor cores. You can see that we've gone from about 60 million. This number is wrong here. I don't know where this is coming from. This was about 20-something million to about 300 million. So that's some pretty impressive growth within 8 years. Now, the portion of the portfolio that I want to focus on today, though, is to tell a little bit more about what happens here in this area, what is the physical layer interfaces. That's the stuff which is driven by, or which is actually analog. So this is driven by analog and mixed signal design techniques. And you find there's a number of those areas where you find this. What's important for us are the physical layer interfaces for interfaces like USB or like PCI Express or like DDR, but also A to Ds and D to As, or things built around A to Ds and D to As, like audio codecs or things like LTE front ends, etc. So what's driving all of this? What's driving the problem? Well, what's driving our portfolio is two things. Number one, and we don't decide these things, the industry keeps on marching on. And these decisions are fundamental for us. We need to make sure that we have the right stuff available in the right process node at the right time. So you have two things going on. Number one is that the industry needs to continue increasing the ability to pump data in and out of the chips. And the number of pins that you can grow in a chip is limited. If you need to increase the amount of data that you move in and out of the chips, you'll have to figure out how you can get more data in and out through the same pin. So you need to grow the bandwidth. And that's really, all of this happens on lockstep. You have higher processing capabilities on the chip. You need to get data moved around on the chip faster. You need to get data on and off the chip faster. And we kind of go by speed levels. You think, so for a while you hear things about DDR, and funny-wise there's an interface called PCI Express. Then you move to DDR2, you have an interface that's called PCI Express Gen 2. You move to DDR3 speeds, and the interface is called PCI Express Gen 3. You move to DDR4, and the interface is called PCI Express Gen 4. We're kind of right now getting into this level 4 speed, great as I call it, pretty soon moving towards level 5. And the complication continues to increase, but the fundamental thing is you need to get data faster in and off the chip. And would be, if you could grow more pins, that would be fantastic, because you just add a few more pins, you get extra bandwidth. You can't grow more pins on the chips. We call this chips being path limited. And because of chips being path limited, the only thing that you can do is increase the speed, the transmission speed on the pins themselves. The other thing that happens is that process technology keeps on moving forward. We call this Moore's Law. And what we are plotting here is pretty interesting, actually. What we're showing, the way to read this, so you see all of these waves. The way to read this is that in Q3 of 2003, there were about 120 designs being done in the 90 nanometer process node. And from those 120 designs, the number that had taped out was about 20. That's the pale color. Okay. And the total number was about 120. So about 100 were active. And we count this because as a company, we're pretty much involved in every single chip design in the world. We gather all this data, we compile it once a quarter. There's only one person who knows exactly who are all these customers. And then that person generates the slides and forgets everything. This is extremely sensitive information. But the industry is happy that we compile it and share it with everybody in an anonymous forum, because what it does is it kind of shows what the drumbeat really is, in addition to all of the marketing that happens everywhere. And then we stop counting at some point where we get to 400 designs, 450 designs. It's just too much work to track, right? You say, look, I mean, this is an established node. People know how to do design. Let's just move on. So you can see the different waves. You can see the 90, you can see the 65, you can see the 40, 45, you can see the 28, 32, etc. Interesting things are, what's the adoption of this thing here? Which is, when is the first design being done in a particular node? And that pretty much follows Moore's law. People talk about the fact that this is slowing down. Not really true. From a technology point of view, so far, we've pretty much been able to stick on the drumbeat of the production of Moore's law. What has changed, though, is the pace of adoption, not by the very early guys, kind of the Intels of the world, but by everybody else. And the way that this manifests itself is the amount of time that passes from reaching somewhere at 300, 350 designs across the industry. You can see that the time from here to here is much longer than the time from here to here. Now, there were a number of issues that made this a little bit complicated. You may have been hearing that TSMC had a lot of yield issues on the 40 node. The ramp up of 28 wasn't that difficult. I think the ramp up of 20, whether it's planar or FinFET, is really going to be fun. Interestingly here, actually, there is, for those of you who are curious about what's the newest and what's the latest, we have counted 1 or 2 chips being done in 10 nanometers. Those are test chips. And so where are we? Well, you know, we have a bulk of a design in the 28 nanometer node. And when we say we have a bunch of design, we have had customers who have designed in more than 100 of our titles in the meantime. And this was a long time ago, at least in terms of process geometries. This is a long time ago, September of last year. Let me tell you, not many people get excited within Synopsys about taping out another chip in 28 nanometers. And we get prices, and TSMC is very happy because since we have a lot of IP, they can get customers to design and tape out a lot of chips themselves. All very nice. But let's look now into what it means for 20 nanometers. What's happening there? Let's get into the meat of all this. Well, there's a bunch of challenges that you have in 20. The design rules for manufacturability in 20 nanometers have become extremely complex. And obviously, the impact of those is area and is development time. Stuff does not get easier to do in 20 nanometers. The design rules are very, very restrictive, and many times what they do is they force you to just design stuff bigger. Now, designing stuff bigger when you're going to a small geometry is pretty bad. right? Because the logic portion of that, the digital portion of it, is going to be shrinking. Right? You're going from 28 to 20. A transistor is smaller in 20 than it was in 28, so the density increases. So what was 2 square mil last time now gets to about 1 square mil. Okay, that's great. If you had some analog stuff that was 1 square mil, and that now, because it's getting more difficult, is actually growing to 1.1 or 1.2, that's a total disaster, because the expectation is that everything is going to get smaller because the silicon is also getting more expensive. So analog things getting bigger because, oh, hey, this is just more complicated and the design rules for manufacturability make it more difficult is not acceptable. At the minimum, you have to stay at the same side despite of all the trouble. In fact, what you want to do is also be able to make it smaller. So the solution for this is just new architectures. You need to come up with new architectures for the circuits and for new architectures of the whole functionality. And in particular, from the very beginning, you need to take into account the actual flow plan. So where is this block going to end up on the chip later on? Funny thing is we need to kind of anticipate where customers would like to put that particular type of blocks on their chips, which we have no idea what they look like. Okay. Now the other thing that happens is that people continue to standardize building blocks. I talked about PCI Express Gen 1, PCI Express Gen 2, and Gen 3, and Gen 4. What's driving this is just the needs from the architectural level, from the system level perspective. And the spec goes from 3 gig, from 2.5 gig, to 5 gig, to 8 gig. And let me tell you, those guys don't care whether the implementation technology for doing this is available or not. And they end up specifying things that are just very, very difficult to do with the lower I/O voltages that you find from generation to generation to generation. So a long time ago, something called USB was specified, and there were some 5-volt tolerance that was expected, and the I/O voltages were 3.3 volts, and you could do that. Well, then they spec'd out 3.0, increased the speeds, process technology kept on going down. Your I/O voltages today are 1.8 volts. The spec for USB doesn't change. It's like, well, go and figure it out how you implement 5-volt tolerance. Your problem. Right? So the system needs are completely uncorrelated to the actual silicon capability. The silicon capability just marches on, and the engineers have to figure out how do you bring this, again, into some sort of balance. So other things is that obviously the core devices, so the transistors themselves, just keep on getting worse and worse and worse. We make them smaller and smaller and smaller, and they behave less and less like transistors. Now, in the case of digital, again, the tools take care of a lot of these problems for you. In the case of analog, as an analog designer, you are just left with this new transistor that truly just sucks. And you have to figure out how you're going to be able to make this work. So tremendous amount of smartness has to go to that. And again, the solution is you need to come up with new architectures who are just able to implement functions with transistors that continue to have smaller and smaller dynamic range. And last but not least, as I was saying, the companies don't really care. You're going from the 28 nanometer node to the 20 nanometer node. The digital portion, the same functionality in 20 is smaller than in 28. The expectation is that you're also going to figure out how you can make the analog functionality smaller. Although the process doesn't do anything for you in that sense, right? I mean, so the solution to all of this is really to come up with new architectures. It's the only way that you can compensate for the badness of moving to the next process node. And this is just smart engineering. So what are all the things that you have to deal with? Well, you have to deal, as you're starting to go smaller and smaller and smaller, this is really the alphabet soup of effects that start happening and you start seeing in the silicon. And all of them are bad. None of these things is really good for you and make your life easier. The worst thing about all of this is that early on in the process lifetime, nobody really knows what these effects really do. Of course, we do a lot of device simulation. So companies like foundries like TSMC or Global Foundries or the big IDMs like Intel, they start creating first mechanical models of the transistors, and then they do 3-dimensional modeling of start solving a lot of differential equations and try to kind of anticipate what the actual model or what the actual characteristics of those transistors will be once implemented. But nobody has a clue. So the only way that you can figure out what the silicon really does is you build test chips. And it's the same thing that always happens in engineering. You do an experiment, right? And then you have some idea about what it could be, so it's called modeling. And then you do an experiment, and hopefully the experiment kind of validates the model or gives you some feedback as to how you have to parameterize the model and adapt the model so that it matches reality. Of course, you could also try to change reality to match the model, but it ends up being something in between. One thing is called process tuning, the other thing is called modeling, and what you want is really good correlation between the reality and the model. We call this simulation to silicon correlation. Once we have this, then we love it, because then we can simulate a lot and we can kind of predict what's going to be happening in silicon. So what we do is we do chips, test chips. We call them technology assessment chips. Let me tell you a little bit what's the kind of stuff that we put on it. Because obviously early on, it's really difficult to do complex stuff, because you're trying to design complex stuff based on models that you don't know if they're really good. So typically it wouldn't work. So you do simpler things. What you do there is you put very simple things like ring oscillators. These things are great. They're purely digital logic. They really tell you what's the frequency of the process. So it gives you some indication about the speed. We put some DDR4 IOs because we wanted to play with the thick IOs there. A bunch of analog IP also, and then a bunch of test devices that go into this matrix. These are just a bunch of transistors, resistors, and capacitances. You will say, well, why do you put so many in just a few? Well, the reason that we put so many is that we want to actually figure out how these things really behave in silicon depending on a number of things, which I'm going to be telling you more about. And then for those of you who want to know when this happens, well, this really happens early on. We taped this out in 20 nanometers in April of 2012. And this is when the PDK, so the development kit, process kit that you would get from TSMC was about, I think it was in the 0.1 release state, which is the first one that ever gets released. Everybody knows 0.1 means it's really shaky. Try to do some design, but no guarantees for nothing. So what did we put in there? Well, for 20 nanometers, the first thing that happened is that instead of doing single patterning, we had to do double patterning. The reason we have to do double patterning is that on the lithography end, the sizes of what we want to draw are smaller than the sizes that we can actually implement through the lithographic process. So what we do is this is what we can do in lithography, right? So that's the minimum distance that we can actually get onto the chip, right? And then we do it 2 times. We put it once here, then we offset by something, and guess what? Now we're able to put stuff onto the chip that has much smaller distances in between. Problem with all this is that if the mask, and this is being done by having 2 masks set, but if the masks are not fully aligned, the distances here start changing. And things start overlapping better or less good. And this creates a huge problem because it's a new source of variability. And variability is the thing that we don't want, right? Because variability just means that your models get less and less sharp, and they get less and less precise. Now, our question was, how much does this really affect us? So to do this, what you basically do is you put some test circuits on that, and then we put about 1,500 resistors, and capacitances, and we do this with different device matching. So of course, silicon is not perfect, right? So what you try to do is you always try to come up with circuits where the imperfection gets compensated because you match up the devices. One goes and shoots up into the positive direction, the other one goes into the negative one, and then hopefully the whole thing just kind of balances itself out. But we're talking now about having 2 devices, playing the trick with 2 devices, compensating for imperfections or variability by having 2 devices, and making sure that things compensate each other. If, because of double patterning and density effects, those 2 devices, there's some other effect laid on top of that, things are getting really complicated. So what we did is, that's the matrix, basically, of those devices. And then you take those devices here. These are really the ones that you want to kind of use as matched devices, so you hope that they're going to be matching. You put some dummy stuff in between there to isolate it from the next set of devices. And then you start to run basically transistor characterization curves and all that. And you do this, you start stepping through that, both for the NMOS as well as the PMOS devices, right? And you sweep on the voltage sides and you sweep on the current. And you get this here. And then you continue to do this. You get all these measurement points, and you do it. You start sweeping across this so that you get an understanding as to what's really happening with these devices across the full range of parameters. This becomes a huge amount of data, as you can imagine. And what we have to do then is basically write software that starts extracting the actual information from this to tell us what's really happening. Now, the reason this is becoming interesting is that there's one thing that's called density filling. You need, in order for something to be manufacturable, you need a certain density of material. But the density, the foundry tells you, look, I mean, the minimum density that you need is 26%, the maximum density is 58%. As long as you meet that, we can manufacture it. But this difference of 30% now becomes a killer on the design side again. Because depending on what the density in a certain area is, the devices behave differently. And if you're now doing some matching, you're using device matching techniques in order to compensate for different effects, but those devices are sitting in different parts of the design with different densities, then the whole thing goes kaput again. Funny thing about all this, you design your things, you map your devices on the chip, but you have no idea what the density is going to be at that point. Because the density depends on other stuff that's around it that you may not have designed. And the density filling, in order to match the manufacturing rules, happens at the end of the process. At the very end of the design process, you do the density filling. So suddenly, once you're done, you start changing things that have impact again on the stuff that happened all the way at the beginning. That's exactly what you don't want to have in design, right? What you want to have in design is something that looks more like the waterfall thing, where you kind of, if you have to reiterate, you go up or down one step, right? You fix this here, and then you go to the next one. You want the smallest iteration loop as you can. You never want an iteration loop that goes across the whole thing, because that means just redoing all your work. The problems with density fills that are just becoming extreme as you're starting to move into 20 and into 14 put a tremendous amount of pressure on analog mixed signal designers who have to anticipate all the badness that could happen maybe later on. So you need to design much more robust circuits, and you have to be very, very careful from the very beginning as to where you're placing things. One example, for instance, is, no, I'll talk about this a little bit later. Okay. So is it possible to do design under all these constraints? Absolutely, yes. These are just some layouts of some chips that we did lately in 20 nanometers. So this is not 28, this is 20. Things got more complicated, as you can imagine. And actually, these chips do work. And this is, again, these are probably some of the first chips in the industry that have been done in the 20 nanometer node where silicon is back and is working. And it's not just digital stuff, it's mostly just analog mixed signal stuff. So that's quite good and quite impressive. So it's possible to do it. So how do you do this? Well, the way that you do this is, number one, you need very smart engineers who are able to come up with robust circuit architectures and have a full understanding of all the effects that can happen through the manufacturing process. And then the thing that you do is you resort to a lot of verification or simulation. And it's not just you have to, you can see a litany here of different things that you have to do. You have to simulate for first order effects, which everybody does, but the second and third order effects are becoming more and more important. So you have to compensate for all of these things. There's you have to take into account, I can only overemphasize that, not overemphasize that, you need to have robust design techniques. You cannot design for a particular process point. You have to assume that stuff will change. Variability is becoming larger and larger. It's all about figuring out how you design functionality in a way that's robust against the variations that you're going to be encountering. And last but not least, you have huge problems also with reliability. Things will change in the lifetime of that device. Electrons and holes will be moving around because the materials that are being put into those devices will be diffusing from one layer into the other one. It's very little. But we're having so few atoms in the meantime in these layers that just a few of them actually moving through the different layers start creating huge problems. So you need to take that into account because the reliability will be impacting the lifetime of the product, and that's going to be having a tremendous economic impact on the end customer, who potentially sees after a year or two a bunch of stuff being sent back to him because it stops working. That gets extremely expensive. Okay, and last but not least, you do all of these things by simulation, but last but not least, you have to build it because you're making a lot of assumptions, and you need to make sure that those assumptions are right. And that's what we call silicon validation. So you build chips, actually. Now, in terms of how much effort goes into this here, well, this is just one example. Just the simulations of a particular PCI Express PHY take us about 13 CPU years. So this is about 13 CPUs running for, this is 13 CPUs running for a year. And obviously, we don't have time to run in a year. We need to have the ability to rerun complete regressions within a couple of days. So you start to have an idea about what you need in terms of these of infrastructure. And of course, I mean, we have huge CPU farms, as you can imagine. But the advent of things like cloud computing are fantastic because smaller companies may need just this many CPUs for 3 hours. Being able to rent them is a great deal compared to having to kind of buy them and just use them every couple of months. But again, the compute intensity of this continues to grow, and I see no end to that. Of course, we're trying to become smarter, but the number of effects that we have to simulate is becoming larger. So I talked about scaling, and this is an example for scaling as to what's possible. This represents the layout of our PHY, of our USB PHY in the 130 nanometer node. This is a long time ago. We were using 3.3 volt IOs, or thick oxides, for doing the design, and 1.8 volt core devices. For an analog designer, this is heaven. Real 3.3 volt devices with some nice headroom in there, my God. I mean, it's bulk CMOS, but you still feel like you can do something in analog. And this was the size of it in 130. Then we went to 65 nanometers. And this is exactly what I was saying. I mean, if you just take your design in 130 and you try to kind of map the layout, right? You move the layout from 130 to 65, it doesn't get any smaller. It probably won't work, right? But then you could think, well, I'm just going to be keeping the overall architecture, the overall layout. I'm going to be playing around a little bit with the devices. I'll make it work somehow. This doesn't fly. And the other thing is not acceptable because everything else got smaller. So the guy in charge of the SoC says, I want the analog to also get smaller. And you can do it. You just have to re-architect things, and you can figure out how to make it smaller. And the green is the size of the new one. Then when we moved to 40, and for 28, we were able to again be a little bit smarter and just make a smaller one again. And last but not least, when we went to 20, we were able to shrink it again. So over time, through architectural changes, we've been able to basically take this functionality called USB 2, where most people said, look, I mean, it's analog design, it doesn't scale. Analog design, if you're going to smaller geometries, will just get bigger and bigger and bigger relative to the whole thing. We were able to pretty much make this thing shrink. Now, it did not shrink as quickly as the digital portion, but we were able to shrink it nevertheless. And this is actually, you can do this for pretty much all of the PHYs. We've been doing it for PCI Express, we've been doing it for USB. This is all engineering smartness. It's all against the process. The process, in fact, are just making it bigger. Now, other things that you have to take care of is, for instance, in the case of DDR. So if you look at what's happening in memory interfaces, we need to get data on and off the chip faster, right? There's a limit to what we can do there. And the way that this that's actually what the speeds that you want to achieve is the red curve here. So you want to go from something like 200 megabits per second all to 3.2 gigabit per second, which is the speed at which DDR4 is running or will be running. How do you do this? Well, the core frequency, so the frequency of the actual digital portion of that, you can see it's only going up from 100 to 200 megahertz. And then, but this here is going higher. So how do you do this? Well, the way that you do this is that you actually change the size of the prefetch. You make the you keep on getting bigger, more and more bytes out of the memory at the same time. and you're doing that at the same frequency. If you're doing this, and obviously the bandwidth is the multiple of that, and that's the way that we've been able to get more stuff in and out, while at the same time not changing while at the same time not having to drive the clock frequency higher. This is also a form of architectural scaling. You change the architecture of the way that you get memory in and out, the way that you get data in and out of the memory, by architecting the mechanism in a different form. Now you could say like, well, okay, so I understand, in the case of USB, you did some magic. In the case of DDR, what you did is instead of getting 1 byte at a time or 2 bytes at a time, you go to 4, you go to 8, and bring this whole thing in. Of course, it's going to run faster. Okay, got this. Funny-wise, you can also do this in areas where you think there's going to be much more, that's not possible, in the area of data converters, for instance. And you're able to do this even by working through all of the issues that you have in terms of the I/O, the thick oxide devices, which are the ones that you actually use for doing analog design. To get a sense for the magnitude of this here, the supply voltages have pretty much halved from 65 to 20. This is a huge compression of the dynamic range, of the useful range that you have in the transistor device, to be able to do any work there. And techniques that you use, that we've been using in this year, are things like clock boosting, et cetera, et cetera, et cetera. And the effects that we're encountering now when we're moving to FinFET again are just an order of magnitude worse than this. But somehow through engineering creativity, we're able to continue to compensate for all the effects that are being thrown at us on the silicon side. So then next question, of course, is it possible to do design in even smaller geometries? And the answer is absolutely yes. These are some examples of chips that we've been doing lately in FinFET technology. And this is one where we have a press release about. There's a bunch of other things where we don't have press releases. So it's possible to do. But there's yet another thing. I've been talking mostly about the fact that, hey, look, it's getting more and more complicated as you're going down the process nodes. The technical difficulty is increasing. But at the same time, the requirements from a systems perspective keep on getting more complicated. The speed keeps on increasing, and customers want you to make the design smaller, despite the fact of things getting more complicated. There's another effect that's happening. So things are becoming more difficult. You need to invent new things in order to be able to deal with the process complications. On top of that, the systems guys keep on increasing the requirements. The speed has to keep on continue to go up, which makes your job more and more difficult. On top of that, what's happening is that the time that companies like, let's say, Qualcomm or Apple or Samsung, who are playing in the mobile space, are confronted with, is that they have to be able to take new process capability and build new products based on that on smaller and smaller amounts of time. So that's what's called schedule compression. You used to do a chip in about 12 months of design, 6 months of fab cycle, plus characterization, total of 18 months, and then you start to have something where you go like, okay, look, we may have to fine-tune something here and there, the thing goes into production. We've gone from 12 plus 6 to 6 plus 3, so to 9 months. In the meantime, these companies need to get a chip out in 9 months. Okay, the only way that you can do that is by starting designing very, very, very early, when basically TSMC gives you a design kit at the 0.1 release level. And then hopefully by the time that this whole thing becomes 1.0, which means you can go ahead and manufacture, you have your design finished. Now imagine us as an IP supplier. Ideally, we are finished by the time that our customer starts designing. But us finishing, if our customer starts designing at 0.1, we would have to start designing at -1. Well, that doesn't work. So we also start designing at 0.1. So now our customer is designing their chip at the same time that we're designing our IP. And they want to use our stuff in their design. This creates a set of complications here. And what ends up happening is that the only way that you can handle this is by aligning fully with the foundry. So we have to work, for instance, very closely with TSMC, with whoever their first customer is, in order to make sure that whatever we develop at any point in time fits exactly with what TSMC is able to support and what our customer needs. And pretty much we finish something and our customer is designing that in the day later, right? And this is very different from the way that we used to work in the past, which is we just do our stuff at our pace, the way that we want to do that, because it makes sense to our engineers. And when we're done, we give it to our customer and tell them, don't worry, everything is perfect. These days, the way that we have to operate is we do stuff at the pace that our customers need us to do it, give it to them when it's completely immature. They know that, or at least they pretend that they know that, until it doesn't work. Then they tell you, well, but why isn't this working? I say, well, we both knew it wouldn't work, right? That's what we agreed on. Oh, yeah, but you wanted it really early, right? Oh, yeah, I remember that. But it doesn't work, right? So you have to start working on intermediate deliverables all the time. And the most important thing is everybody has to share with everybody about what are your assumptions and what are all the things that you know are not working yet. Because the next party is basically relying on that. So you have to play completely transparent, and you have to do this across companies. That makes things very interesting and very funny. So just to conclude this, I think the first insight that we have is because of the physical effects, in particular density. I cannot emphasize enough how much density, the fact that density fill happens at the very end screws up what you did very, very early on if you don't think about that. Because of this, you have a much deeper link between the layout and your power performance scenario requirements than in previous nodes. And it's only going to get worse. We found 20 was worse than 28, and 16, 14 was worse than 20. The things that you're dealing now with FinFET is that actually the devices are quantized, right? You know that with fins, basically the way that you control things is pretty much by the number of fins that you put on the whole thing. But this is not that much of a problem in the end. We thought it would be really, really difficult. The quantization of devices has turned out to be more of a scare than an actual issue while you're doing design. But still, the issue that we have with FinFET is that, well, you know, we're going to 14. By the time that we go to 14, stuff is again smaller than in 20. So we have to deal with that, and we also have to deal with the fact that we need new architectures because of FinFET technology for analog. If you're digital, you don't see these things. The tools do the tricks for you. Double patterning has effects, and in particular what it does is it affects, it's again the density that's implied by that, and then the mismatches that it produces for the devices that are sitting underneath it. As I said, FinFET technology just adds one more level of complexity to it. And when you talk about FinFET, always make sure that you distinguish two things. Some foundries have adopted FinFET in the same process geometry than before. So for instance, TSMC calls it 16 FinFET, but 16 at the metallization level is still 20. So in a way, the moving from 20 to 16 FinFET only adds the problem of FinFET. It does not add the problem of going to a smaller geometry. 16 is only smaller in marketing terms compared to 20. Okay? But if you're going from 20 to 14 at Samsung, for instance, that's real 14, and it's FinFET. So suddenly you have to deal with the fact that you're moving from the 20 nanometer node to the 14, which is more like 16 actually. And on top of that, you have all the complications coming from FinFET. So you're taking two steps at the same time. Handling two steps, two differences at the same time in design is really, really calling for trouble, or at least calling for a lot of difficulty. That's always solvable, but that introduces a tremendous amount of risk. And last but not least, all of these things are happening while the schedules are compressing. And this requires a completely different way of developing things. It's no longer about doing things in the most efficient way for the development of the actual IP. It's developing things the most efficient way so that the first customer of the foundry is able to get a product out, because that's when everybody starts making money. And that's a completely different set of optimizations that you have to do. And that change in mindset for the engineers, for the designers is tremendous. Because as a designer, you don't want to redo things. As an engineer, you want to get something done, nail it, right, and then you move on to the next thing. The last thing that you want to hear is that your manager tells you, well, we're going to be redoing this 3 times because we need to ship something to somebody else before it's finished. And with this, I would like to conclude. Thank you.